Visit structuralcentral.com to quickly generate structural engineering calculations like those discussed here.
Hello engineers! Today I'm going to show you how to determine the strength of the bolts in steel connections. Steel structures are made up of many members that are small enough to be easily shipped and stored. These members then get connected together on the construction site. Using bolts in these connections is generally preferred to welding due to the speed that they can be attached. So if you're going to be designing steel connections, you're going to want to know how to determine the strength of the bolts. Now let's get into it. There are three limit states that must be considered for each bolt in a connection: bolt shear, bearing, and tear-out. I'm going to show you how to calculate the capacity for each of these limit states. Then I'll show you how to determine the combined capacity for all the bolts, accounting for each bolt's controlling limit state. First, we'll start with the bolt shear limit state. When a force is transferred from one steel element to another, it will be carried across this plane through shear stress in the bolt. The shear strength of the bolt can be determined using equation J3-1 of AISC 360, which is the specification for structural steel buildings found in the back of the steel construction manual. It says that the shear strength Rn is equal to the nominal shear stress FNV times the area of the bolt AB. To get the nominal shear stress FNV, you take the minimum tensile stress FU, which comes from the ASTM specification used for the bolt material, and then multiply it by these three factors. 0.625 is the ratio of the ultimate shear stress to the ultimate tensile stress. 0.9 is a factor that accounts for an uneven distribution of load due to differential strain and second-order effects. If the connection is end-loaded and greater than 38 inches long, it is decreased instead by a 0.75 factor, since the bolts closest to each end will support a disproportionate amount of the load. The final factor of 0.8 accounts for the reduced area of the bolt at the threads. If the threads will be excluded from the shear plane, then this factor can be set to 1. It can be difficult though to ensure that this is done correctly for every single bolt, so many designers choose to just always use 0.8. If you combine all of the factors, you end up with these two equations, which will give you the values for FNV that are shown in table J3.2 of AISC 360. The next factor in the shear strength equation is for the area of the bolt. The formula is just pi times the diameter squared over 4. For the diameter, you get to use the full thickness of the unthreaded region of the bolt. This is the case even if the bolt shear has to be transferred through the threads, since this was already accounted for when FNV was determined. You then include your LRFD or ASD safety factors to get the design bolt shear capacity. You can also multiply this by 2 if the connection is configured so that the bolt is in double shear, which means it transfers the force through 2 separate shear planes. Now we're going to move on to the next limit state, which is for bearing. For the previous limit state, we determined how much force the bolts are capable of supporting. For the bearing limit state, we are making sure that the material around the bolts is strong enough to be able to get the force into the bolts. If the steel is not thick enough or strong enough, there will be too much stress concentrated at the edges of the bolt holes. This will result in deformations and the holes will become distorted, which is called ovalization. Checking the bearing limit state ensures that the amount of deformation will be limited to an acceptable amount. The bearing strength Rn is determined by multiplying a coefficient C by the bearing area, which is the bolt diameter times the bearing material thickness, and the steel strength of the bearing material. The coefficient C will be 2.0 for long slotted holes if the slot is oriented perpendicular to the direction of force. For other hole types, the coefficient will be either 2.4 or 3.0, depending on if bolt hole deformation at service load is a design consideration. The formula will then match equations J3-6A, B, or E found in AISC 360. You then include your LRFD or ASD safety factors to get the design bearing capacity. Finally, we're going to discuss the last limit state, which is for tear-out. The limit state is similar to the bearing limit state in that you are making sure that the force can be transferred into the bolts, but it differs in how it fails. Tear-out occurs when the shear stress adjacent to the holes causes the steel to rupture from one bolt hole to the next or all the way to the edge of the steel. It is essentially a block shear failure with 2 shear planes. The formula for the tear-out strength Rn includes a coefficient C, which is multiplied by LC, which is the clear distance from the edge of the hole to the edge of the connected material or the adjacent hole, times the connected material thickness and the steel strength of the connected material. don't forget that the bolt hole is larger than the bolt diameter, even for standard holes. Similar to the bearing limit strength, the coefficient C has 3 different values depending on the hole type and if bolt hole deformation at service load is a design consideration. The formula will then match equations J3-6C, D, or F found in AISC 360. The LRFD or ASD safety factors for tear-out are the same as they are for bolt shear and bearing capacity. Now that you know how to determine the strength for each limit state, we can discuss how to account for all of them when determining the total strength of the bolts. Say you have a single angle connection that is bolted at the beam. If you have a single row of bolts with standard holes that are located 3 inches from the support, an eccentricity does not need to be considered. The beam end reaction will get split up amongst all of the bolts. The beam steel around each bolt hole must be capable of transferring the force into each bolt, meaning there is sufficient bearing and tear-out capacity at the beam. Each bolt must then be able to transfer the force from the beam to the angle through bolt shear. And finally, the angle steel around each bolt hole must be capable of transferring the force from each bolt to the angle. Since a complete load path is required for each bolt, this means the capacity of each bolt will be the minimum of the bearing and tear-out capacities at the beam, the bolt shear capacity, and the bearing and tear-out capacities at the angle. It is likely that some bolts will have higher capacities than other bolts since they have different clear distances. It is acceptable for these bolts to transfer more of the beam reaction than the weaker bolts. What is not permitted, though, is determining the capacity of the bolts by adding up the capacities of any of the 5 limit states independently. The controlling limit state may be a combination of several different failure modes, so if you're using design tables that only consider the angle size and not the beam size, it is possible that you could end up overestimating the capacity. If you would like to easily create bolt capacity calculations that consider all of the limit states discussed here, visit structuralcentral.com. There you will be able to quickly generate structural engineering calculations just by entering a few inputs. With its intuitive interface and live updating, you will be able to start getting results immediately. Choose your connection type, then enter the dimensions directly on the drawing, and see the connection strength and the strength of each of the limit states right there. The program supports multiple rows of bolts, different bolt hole types, and slip critical connections. Provide the beam reaction, the program will also check its stress ratio. The calculations are well referenced with values plugged in just like you would write by hand. You can also move the mouse over the variables to see a description of what they are and see all other instances where they are used, making calculation review a breeze. Head on over to structuralcentral.com and sign up for free today.